Yeah, because I understood it as an interactive exchange, so I don't want to go so much in detail. I just had the idea to present a little bit how's the situation in Austria, especially in Vienna. What types of buildings we have, what is mostly our task, what we have to do there. So our company, KPPK, is consulting engineers for civil engineering. We are not only doing structural engineering, building services, fire protection, and everything. And so mostly clients want to have the whole field of engineering when they are coming with a project to us. The typical masonry buildings in Vienna, I mean, I'm just talking about 80 or 90%, are mainly built around 1880 until 1920. And they are typical construction parts: arched ceilings, masonry above the cellar normally. And in upper stories, mostly you have wooden beams and walls, of course, masonry walls. Sometimes there have been changes, but mostly you find buildings like that. And then our planning tasks consists also mostly of typical things: removal of walls, addition of an elevator or parking garage, and of course, last but not least, the attic conversion, which is the most typical thing. And addition of elevator and parking garage is coming mostly together with it, because this is bound together from the authorities. Because if you want to build up a attic conversion, it is a must that you have to build an elevator and parking garage also. So that means in that case you have to take care of all of these parts. The material part is mostly tested in situ tests. Sometimes they're also taking some parts of the bricks and the mortar, but it is mostly done in situ test. And you can see these are more or less the characteristic value I was writing there, which we found here. To typical floor plans, this is the most standard case, you can say, where you have the outside walls. Street wall is one here. Then you have a middle wall and the back wall, you can say, on the garden side or courtyard side. And all these beams, which we have mostly, the wooden beams in the ceilings, are from the outside walls to the inside walls. So that means that walls are the main walls for that buildings. This is the main typical floor plan. And there are slightly some other typical. This is that one. This is like a corner building type, which causes very often here in that corner some problems, in my experience. Next one, which also very often, is the typical two houses with in between the staircase. Then it can be like on the left side, where you have the staircase directly, but then you have a split level between the two houses. And the other possibility is like it is on the right side, where the staircase is rounded, and so you don't have any split level there. So that is what I told before already. The main walls are all the loads going through that main walls. That means, and these secondary walls in the y direction. Main walls, I can add these typical sizes are around 60 centimeters in the upper stories. They will a little bit less, like 45, except middle wall. Middle wall is, you can say, 60 centimeters from the ground floor to the attic level, because there are also chimneys inside very often. So that secondary walls are the walls to the neighbor on that side, which are mostly 30 centimeter, and in the attic level then only 15. And the staircase walls are also like 30 or 45. And then this special thing, these extra walls, which are rectangular to the outside walls, they are very thin walls. They don't take any loads. They're just for the building there in between. And these walls are mostly the important factor. Then there are some different ground views, you can say. This is a combination of the standard one with a small part on the backside. This is a huge type, two buildings with two staircases, or a corner building with a small part on the backside with also two staircases. But all these different ground views you will see are similar in wall thickness and ceilings. Yeah, also with sometimes you will find houses with a courtyard inside and the house is going around. And this is a special big one what is going around and has also a circular corridor here inside what is going around. This means you have this staircase here, a staircase here, and all is connected with one corridor which is going around. Ceiling constructions, we have also very typical wooden beams. Of course, this is the standard which you find in almost every house. These are typical between 20 to 26 centimeters. Sometimes can be also the height a little bit more, 30, but this is really seldom. This is a very massive one. I just put it here because it was a nice picture. This, I must say, is a building which is a little bit older than what I mentioned before. So that is a very massive ceiling. And then we have that Dippelbaum ceiling. I did not translate that because I was not sure was the what could I find in English. That means you have one wood to the other, and they're connected with solid wooden pegs. So that gives that construction a very solid type. They are found. This is found mostly as the last level above the third story or so, you can say. You will find very often this type of ceiling. Yeah, and then we have also sometimes in the later part of the period, you will find not only wooden beams, you will find steel beams, and between that steel beams, you will have the wooden beams. Steel beams then have a distance 3 meters or something like that. So the wooden beams inside that are a little bit smaller than before. Of course, in vaults and arched ceilings of masonry, this is mostly found in the cellar or above the ground floor. Sometimes in bigger buildings, you will find it also in almost every floor, and typically is the ground of the bathrooms or something like that are mostly built up with that ceilings. Yeah, this is also a cellar type vaults, which is typical to find. And then strengthened construction did mostly done by the composite structure of wooden beams and concrete slab, small concrete slab around 8 centimeters, which gives that ceiling a very stiffness, so that you connect here all walls of the building in that area of that ceiling. Then I must say by the authorities until 2008 or so, there was a standard here regarding the seismic loads. And then from 2008 started the area of the EC8. And in the beginning time, it was a very difficult thing with the attic conversion because it was not clear how to do that in a static analysis. And then in 2013, it came the new national annex. And here it was found the possibility, it is similar to the Swiss standard, because all the buildings, they don't have the 100% earthquake resistance. So, or it's really rare to find that. So that means we have to see what's the resistance of the existing building and what's the resisting after the construction. And this is also done before with a reliability analysis. I just try to translate a little bit and put some example. That means you have to calculate a number of persons who are in the building. This is in different categories. Let's say 10 flats, and there are 2.35 persons each flat. And then there's also a time factor, which is in case of the flat is 1. So it means in that building with 10 flats, you have to calculate 23.5 persons. And then you are building up in the attic story 2 flats, let's say, then this will be higher. And this I marked here, there are 4.7 persons more in the building. That means in that standard is saying you have to see what is first the seismic resisting factor, let's say, for example, 40% of the existing building. Then you have a probability of breakdown existing building and the number of persons existing building, which we had here. And then with that curve, which is also like in the Swiss code, you have a correlation between the seismic resistance factor and the probability of a breakdown. And then you're calculating it in that, and then back to the next one, what is the planned situation. And then you have here the number of additional persons again. And with that formula, you get the result, how much you have to strengthen the building. That means your existing building has 40%. With that additional persons you want to, with the flat, put in the building, you have to reach the 44%. So that is mostly the task which has to be done. So that means if I put in one, we have the existing building, the resistance factor, number of additional persons, and a required resistance factor. And then we are calculating the resistance factor. Sorry, I did not translate that. Then we get a resistance factor after changing the building with the additional persons and additional loads from the attic story. And then this must be fulfilled. Then the authority will accept. What I forgot to mention is that here, it is important to know, additional persons is only 50% more than existing in the existing building. So that does not mean you can bring up more than 5 flats in that case extra. Okay, then I'm coming to 2 projects. This is a very typical one, which is now in the authority phase, the permission phase. This is like a typical building. Here you see that existing situation done in Tremuri, and the mesh with the ground view. and we could figure out here the element wall, which was, here comes the building, about 43%, 44% of the earthquake. And then the plan situation. The strengthening was the ceiling above the third floor, because that was also of wooden beams, and there will come a composite wooden beams, concrete ceiling, which is connecting all the inside walls then, and can transport the shear forces from one wall to the next one, and we can activate walls like that or like that. And also, of course, there is a lift here in concrete, which will bring also a positive effect. And then we are calculating that the plan situation, and the same comes also, building will same, only loads will be changed, and the lift is coming, and the ceiling. And you will find the important element here, and we could raise up around 10% the seismic resistance. Project 2 is a little bigger one and has a longer history. You can see here a little bit on the photos what was the history. They are built up here antenna, and then now it has to rebuild. So that is also the existing situation you see here. Special is that here in that story, there's a big hall, you can say. These rooms are around 7 meters high or so. And then we were again calculating that in the Tremuri. Found there was an existing concrete shaft inside. Found the element. And then here some more strengthening have been done, such as steel frames here in that areas. Ceilings, all ceilings were stiffened with either concrete slabs or composite wooden beams, concrete, or solid timber boards or wooden beams. And also new shafts for lifts were built up inside and connected with concrete slabs to the rest of the building. And then it was also calculated again. You see here these lift shafts inside. And again, we got after that the new seismic resistance. Yeah, and some impressions of that building. Here we can see that we're built in that massive steel frames. Also some injections in some areas with in the masonry walls have done. Here you can see that the beams we leave inside the wooden beams and strengthen it with other wooden beams, and then above it was coming a solid timber board connected with outside and inside walls. Yeah, there were also done a lot of concrete works, because that building had 3 basement floors, which got a garage inside, and then it is the building after all constructions were done, how it is now. So that is more or less on the end. Thank you very much. Thank you very much to S.T.A and Ingwer, which is the distributor of Tremuri here, Austria, Germany, Switzerland, as far as I know.